Imagine a celestial ballet, painting the night sky with hues so vibrant they seem to defy reality. But what if I told you this breathtaking spectacle holds secrets even more serene and captivating than its visual glory? Prepare to drift into a world of surprisingly soothing facts about the Aurora Borealis that will calm your mind and spark your imagination. Hello there, and welcome to 100 Facts Before Sleep. Tonight, we drift into the ancient and extraordinary world of the Aurora Borealis, the deep memory of our planet, written in light across the polar skies. Long before the first humans looked up in wonder, the sun and the earth were already locked in a silent dance. Streams of charged particles traveled across the void, interacting with our planet's invisible shield, painting the high atmosphere with ethereal light. The quiet, dancing lights above you are ancient beyond imagination. And yet, they are still moving, still shimmering, still changing. This is the story of the Aurora, a story of solar winds and magnetic fields, of colliding atoms and cascades of light, of a beauty that takes millions of miles to unfold. Within every shimmering curtain, there are whispers of the sun's power, the Earth's protection, and the silent, cosmic forces that shape our world. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here, too, one sleepy soul at a time. For now, just breathe. Let your eyes grow heavy, and let the ancient, dancing lights of the Aurora cradle your thoughts. Let's begin. The Aurora Borealis is not just a beautiful display. It is the visible result of a colossal, invisible battle, a constant interaction between the energy streaming from our sun and the protective magnetic shield that surrounds our planet. Fact 1. The Aurora Borealis, or Northern Lights, and its southern counterpart, the Aurora Australis, are natural light displays caused by charged particles from the sun colliding with gas molecules in Earth's upper atmosphere. These particles, primarily electrons and protons, are carried across space by the solar wind, a constant stream of plasma flowing outwards from the sun. When this solar wind reaches Earth, it interacts with our planet's magnetosphere, the region of space dominated by Earth's magnetic field. Most of the solar wind is deflected around our planet by this magnetic shield, protecting us from harmful radiation. However, some particles become trapped within the magnetosphere and are funneled along the magnetic field lines towards the polar regions. As these high-energy particles descend into the upper atmosphere, altitudes typically ranging from 100 to 400 kilometers, about 60 to 250 miles, they collide with atoms and molecules of gas, primarily oxygen and nitrogen. These collisions excite the atmospheric gases, causing them to release energy in the form of photons, or light. It is this emitted light, occurring on a vast scale, that we perceive as the beautiful, dancing aurora, a silent luminous spectacle born from cosmic interactions. Fact 2. The different colors seen in the aurora are determined by which specific gas molecules are being excited by the solar particles and the altitude at which these collisions occur. The most common color observed is a pale, ethereal green. This light is produced by collisions with oxygen molecules at altitudes between about 100 and 300 kilometers, 60 to 180 miles. Oxygen atoms at this level, when struck by energetic electrons, enter an excited state and then slowly return to their ground state by emitting green photons. Higher up, above 300 kilometers, collisions with oxygen can produce red auroras. At these extreme altitudes, the atmosphere is much thinner, and the oxygen atoms have more time before colliding with other particles, allowing them to emit light from a different, lower-energy excited state which corresponds to red light. Collisions with nitrogen molecules are responsible for the blue and purple-violet hues sometimes seen, particularly at the lower edges or in the faster-moving parts of auroral displays. Nitrogen tends to emit light more rapidly after excitation, producing blues and purples usually below 100 kilometers or deeper reds at higher altitudes. The specific blend of colors depends on the energy of the incoming solar particles and the composition of the atmosphere at the collision altitude, painting the sky with a silent palette dictated by atomic physics. Fact 3. The sun is the ultimate source of the aurora. The charged particles that create the lights originate in the sun's outer atmosphere, the corona. The corona is incredibly hot, millions of degrees Celsius, and dynamic, constantly releasing a stream of plasma known as the solar wind. This wind travels outwards through the solar system at speeds ranging from 300 to over 800 kilometers per second, about 1 to 2 million miles per hour. However, the intensity and speed of the solar wind are not constant. The Sun goes through periods of higher and lower activity, known as the solar cycle, which lasts approximately 11 years. During periods of high solar activity, solar maximum, events like solar flares, intense bursts of radiation, and coronal mass ejections, CMEs, massive eruptions of plasma and magnetic field, become much more frequent and powerful. These events release huge clouds of energetic particles that travel towards Earth. When a CME hits Earth's magnetosphere, it can trigger intense geomagnetic storms, leading to much brighter, more widespread, and more dynamic auroral displays that can be seen at lower latitudes than usual. The quiet shimmering lights are a direct reflection of the Sun's ever-changing mood. Fact 4. Earth's magnetosphere acts as a crucial protective shield. Generated by the motion of molten iron in our planet's outer core, this magnetic field extends tens of thousands of kilometers out into space, forming a teardrop-shaped bubble around Earth. The side facing the Sun is compressed by the solar wind, while the side facing away is stretched out into a long tail, called the magnetotail. This magnetic field deflects the vast majority of the charged particles in the solar wind, preventing them from stripping away our atmosphere or bombarding the surface with harmful radiation, thus playing a vital role in making Earth habitable. However, the magnetosphere is not a perfect shield. Near the poles, the magnetic field lines curve downwards, converging towards the Earth. These regions act like funnels, guiding some of the trapped solar wind particles along the field lines into the upper atmosphere above the Arctic and Antarctic circles. The aurora occurs precisely where these particles precipitate down, making the magnetosphere not only our protector but also the invisible conduit that channels solar energy into creating the beautiful lights, a silent guardian shaping the cosmic weather around our planet. Fact 5. Auroras occur in oval-shaped regions centered around the Earth's magnetic poles, not the geographic poles. These areas are known as the auroral ovals. The magnetic poles are the points where the Earth's magnetic field lines point vertically downwards, north magnetic pole, or upwards, south magnetic pole. Due to the complex nature of the Earth's magnetic field generation, these magnetic poles do not align perfectly with the geographic poles, the axis around which Earth rotates, and they also wander slowly over time. The auroral ovals are typically located between 60 and 75 degrees of magnetic latitude. Under normal solar wind conditions, the lights are most frequently seen within these ovals. However, during strong geomagnetic storms caused by CMEs or high-speed solar wind streams, the auroral ovals expand significantly, pushing towards the equator. This expansion allows the aurora to be seen from much lower latitudes, occasionally reaching places like the northern United States, Central Europe, or even further south, offering a rare glimpse of this polar phenomenon far from its usual quiet home. Fact 6. The shapes and movements of the aurora are incredibly varied and reflect the dynamic interaction between the solar wind and the magnetosphere. Auroras can appear as quiet, diffuse arcs stretching across the sky, or as gentle, glowing patches. More active displays often feature dynamic, shimmering curtains or rays that seem to ripple and fold as if blown by an invisible wind. Sometimes, the lights form a corona, where rays appear to converge directly overhead, creating a stunning crown-like effect. These shapes are determined by the path of the incoming electrons as they are guided by Earth's magnetic field lines and the specific atmospheric region they are exciting. The rapid movements and flickering often observed are due to fluctuations in the flow of particles from the magnetosphere, sometimes occurring in bursts or waves. Watching the aurora is like observing the subtle shifts and flows of invisible magnetic fields and particle streams made visible by the atmospheric canvas, a silent, luminous ballet governed by electromagnetism. Fact 7. Auroras are not exclusive to Earth. They have been observed on several other planets in our solar system, provided they have both an atmosphere and a magnetic field. Jupiter and Saturn, the gas giants, possess incredibly strong magnetic fields and powerful auroras, far more energetic than Earth's. These are fueled not only by the solar wind but also by particles originating from their volcanically active moons, like Jupiter's Io, or their rings. Hubble Space Telescope images show spectacular auroral curtains dancing around their poles, sometimes visible in ultraviolet light. Uranus and Neptune, the ice giants, also have magnetic fields and exhibit auroras. Even Mars, which lacks a global magnetic field today, has localized pockets of crustal magnetism where faint, patchy auroras have been detected. Observing auroras on other planets helps scientists understand their atmospheres, magnetic fields, and interactions with the solar wind, revealing that this quiet light show is a common phenomenon across the diverse worlds of our solar system. Fact 8. Despite their ethereal, ghost-like appearance, auroras occur at very high altitudes, far above the clouds and weather systems we experience. The most common green lights typically originate between 100 and 300 kilometers, about 60 to 180 miles, above the ground. The rarer, high-altitude red lights can occur upwards of 300 to 400 kilometers, 180 to 250 miles, or even higher. To put this in perspective, the International Space Station orbits at an altitude of around 400 kilometers, meaning astronauts can sometimes fly through the upper reaches of the red aurora or look down upon the green curtains below. Commercial airplanes fly much lower, typically around 10 to 12 kilometers, 6 to 7 miles, far beneath even the lowest auroral displays. This vast distance contributes to the silent, otherworldly quality of the lights, a celestial phenomenon occurring in the near vacuum where Earth's atmosphere begins to merge with space. Fact 9. Historical records and folklore from cultures living within the auroral regions are rich with interpretations of the northern lights, long before their scientific cause was understood. Many indigenous peoples of North America had various beliefs. Some saw the lights as the spirits of their ancestors dancing, while others believed they were torches held by spirits guiding the dead, or even the reflections of celestial beings playing a game. In Norse mythology, the aurora was sometimes thought to be the Bifrost Bridge, a shimmering archway connecting Earth, Midgard, to the realm of the gods, Asgard, or reflections from the shields of the Valkyries carrying fallen warriors to Valhalla. Scandinavian folklore also includes tales associating the lights with herring shoals or predicting weather. These ancient stories reflect humanity's long-standing or an attempt to find meaning in the silent, mysterious, and often awe-inspiring spectacle painting their night skies. Fact 10. Auroras generate radio waves, though these are generally not audible to the human ear without special equipment. As the energetic electrons spiral down the magnetic field lines and collide with atmospheric gases, they emit radio waves across a broad range of frequencies, particularly in the very low frequency, VLF, range. These emissions are sometimes called auroral hiss or chorus due to the sounds they produce when converted into audio signals by VLF receivers, often resembling chirps, whistles, or rushing static. While persistent myths claim the aurora itself can be heard directly as crackling or swishing sounds, scientific evidence suggests this is highly unlikely given the extreme altitude. Perceived sounds might be subjective auditory illusions, psychoacoustic effects, or potentially related to electrical phenomena occurring much closer to the ground during intense displays. But the aurora's true voice is primarily in the silent realm of radio waves. Fact 11. The energy involved in a major auroral display is colossal, yet it represents only a tiny fraction of the total energy carried by the solar wind hitting Earth's magnetosphere. A bright aurora might involve power levels comparable to the total electrical generating capacity of a large country, perhaps tens or even hundreds of thousands of megawatts. However, this energy is spread out over a vast area and occurs at extremely high altitudes in a near vacuum. The light itself is diffuse and cold. Despite its fiery appearance, the aurora adds negligible heat to the atmosphere or the ground below. The energy originates from the kinetic energy of the incoming solar particles, which is converted into light through collisions with atmospheric gases. It's a quiet, luminous transformation of energy that has traveled 93 million miles from the Sun, finally revealing itself as a gentle cascade of photons in our upper atmosphere, a silent testament to the immense power flowing constantly through space. Fact 12. Predicting the aurora is a complex science involving monitoring the Sun and the space environment between the Sun and Earth. Satellites like NASA's Solar Dynamics Observatory, SDO, constantly watch the Sun for activity like CMEs and solar flares. Other spacecraft, such as the Deep Space Climate Observatory, SCOVA, positioned at the L1 Lagrange point, about 1.5 million kilometers towards the Sun, act as early warning systems. SCOVA measures the speed, density, and magnetic field orientation of the incoming solar wind about 30 to 60 minutes before it reaches Earth. A key factor is the orientation of the solar wind's magnetic field, specifically its north-south component, BZ. If the solar wind's magnetic field points southward, negative BZ, it effectively cancels out a portion of Earth's northward-pointing magnetic field on the sunward side, allowing much more energy and particles to enter the magnetosphere and fuel stronger auroras. Scientists combine this satellite data with ground-based magnetometer readings to issue forecasts, predicting the likelihood and intensity of auroral displays hours or days in advance, a quiet forecast for a celestial light show. Fact 13. The study of the aurora has a long history, evolving from mythological explanations to scientific understanding. While ancient cultures observed and interpreted the lights, systematic study began much later. In the 17th and 18th centuries, astronomers like Pierre Gassendi, who coined the term Aurora Borealis, and Edmund Halley began to document and speculate about their nature, often linking them to Earth's magnetic field. Christian Birkeland, a Norwegian scientist in the late 19th and early 20th centuries, conducted pioneering experiments simulating the aurora in his laboratory using a magnetized sphere, a ethereal, in a vacuum chamber bombarded with electrons. He correctly proposed that electrons from the Sun were guided by Earth's magnetic field to the polar regions. It wasn't until the space age, with rockets and satellites able to directly measure the particles and fields high above the atmosphere, that Birkeland's theories were fully confirmed, revealing the complex plasma physics underlying this beautiful, silent phenomenon. Fact 14. Sometimes, during particularly intense geomagnetic storms, auroras can exhibit pulsating patches or flickering effects. Pulsating auroras appear as diffuse patches of light that rhythmically brighten and fade, often with periods of several seconds to tens of seconds. They tend to occur towards the end of an auroral substorm, often in the morning hours. The exact mechanism causing these pulsations is still debated, but is thought to involve wave-particle interactions in the magnetosphere, scattering electrons into the atmosphere in periodic bursts. Flickering auroras, on the other hand, show much faster, more chaotic intensity variations, sometimes flickering hundreds of times per second, often appearing as fine, rapidly moving rays within auroral curtains. This is thought to be related to different types of plasma waves accelerating electrons at lower altitudes. These rhythmic and chaotic variations add another layer of complexity and beauty to the display, a silent, flickering heartbeat within the larger auroral forms. Fact 15. The magnetotail, the long, stretched-out portion of Earth's magnetosphere extending away from the Sun, plays a crucial role in powering intense auroral displays known as substorms. The solar wind constantly drags Earth's magnetic field lines downstream, stretching them out like rubber bands in the magnetotail, storing enormous amounts of energy. Periodically, these stretched field lines can become unstable and snap back towards Earth in a process called magnetic reconnection. This sudden reconfiguration releases the stored energy, accelerating vast numbers of trapped electrons back towards the planet's night side. These energized electrons then stream down the magnetic field lines into the polar atmosphere, causing a dramatic brightening and expansion of the aurora, often appearing as a sudden surge of light and activity spreading across the night sky. This magnetotail reconnection is the engine behind the most dynamic and widespread auroral substorms, a quiet buildup and sudden release of magnetic tension. Fact 16. While the classic aurora occurs in ovals around the magnetic poles, other, rarer types of auroral phenomena exist. One example is the theta aurora, which occasionally appears as a distinct arc of light stretching across the center of the polar cap, connecting the dayside and nightside parts of the auroral oval, making the overall shape resemble the Greek letter theta, theta. Theta auroras are associated with periods when the solar wind's magnetic field has a strong northward orientation, positive BZ. Under these conditions, magnetic reconnection can happen differently, allowing solar wind particles to enter the magnetosphere over the poles and create this unusual transpolar arc, a quiet streak across the normally dark polar heartland. Fact 17. Another recently studied atmospheric light phenomenon, sometimes associated with auroras but distinct, is STEVE, strong thermal emission velocity enhancement. STEVE typically appears as a narrow, mauve or purplish ribbon of light, often accompanied by green picket fence structures. Unlike traditional auroras caused by particle precipitation, STEVE seems to be a thermal emission from a stream of very hot, fast-moving plasma flowing in the ionosphere at lower latitudes than the main auroral oval. It's often observed during geomagnetic disturbances, but its exact formation mechanism is still under active investigation, highlighting that even familiar skies can hold new, quiet mysteries revealed through citizen science and dedicated observation. Fact 18. Taking photographs of the aurora requires specific techniques due to the low light levels and movement. A camera with manual controls is essential. Key settings include using a wide-angle lens with a large aperture, e.g., f2.8 or lower, to gather as much light as possible, setting a high ISO sensitivity, e.g., 1600 to 6400, depending on the camera and aurora brightness, and using a long exposure time, typically between 5 and 30 seconds. A sturdy tripod is crucial to prevent blurring during the long exposure. Focusing can be tricky in the dark. Setting the lens to infinity manually, and perhaps adjusting slightly based on test shots, is usually necessary. Capturing the aurora is an exercise in patience, waiting for the lights to dance and adjusting settings to best capture their silent, fleeting beauty against the starry backdrop. Fact 19. The aurora itself poses no direct danger to people on the ground. The collisions happen far too high up in the atmosphere, 100+ kilometers, for any harmful particles or radiation to reach the surface. The light emitted is cold and diffuse. However, the underlying geomagnetic storms that cause intense auroras can have significant effects on technology. These storms induce electrical currents in long conductors, which can disrupt power grids, causing blackouts, interfere with radio communications and GPS signals, affect satellite operations due to atmospheric drag or electrical charging, and potentially increase corrosion in pipelines. While the lights themselves are a harmless and beautiful spectacle, the invisible magnetic disturbance driving them is a powerful force that modern society must monitor and account for, a silent threat to our technological infrastructure. Fact 20. The aurora is a visible manifestation of space weather. Just as we have weather on Earth, wind, rain, temperature changes, space also has conditions driven primarily by the sun's activity. Space weather encompasses changes in the solar wind, the magnetosphere, the ionosphere, and the thermosphere. Auroras are like the rain of energetic particles in the polar regions, driven by the winds and storms originating from the sun. Understanding and predicting space weather is increasingly important for protecting our technological systems, both in space and on the ground. The beautiful, quiet dance of the aurora serves as a constant, visible reminder of the dynamic and interconnected environment stretching from the surface of the sun to the upper atmosphere of our own planet. Fact 21. The most dynamic and often breathtaking auroral displays occur during auroral substorms. These are not like weather storms on Earth, but rather cyclical events of energy storage and explosive release within Earth's magnetotail, that invisible magnetic structure trailing behind our planet. Imagine the magnetotail as containing magnetic field lines stretching out from Earth, constantly being pulled and elongated by the passing solar wind, much like stretching a rubber band. This stretching process stores immense amounts of magnetic energy. When the stored energy reaches a critical point, or when triggered by a change in the solar wind, the stretched field lines suddenly snap back towards Earth in a process called magnetic reconnection. This reconnection acts like releasing the stretched rubber band, converting the stored magnetic energy into kinetic energy, violently accelerating trapped plasma particles, mostly electrons, back along the field lines towards Earth's nightside polar regions. This sudden, intense influx of high-energy electrons causes the aurora to dramatically brighten, expand rapidly towards the equator and poles, and exhibit fast, dynamic movements like shimmering curtains and rays. This explosive phase typically lasts for tens of minutes, followed by a slower recovery phase where the aurora may become more patchy or pulsating as the magnetosphere settles back into a quieter state, ready to begin storing energy once more. The entire substorm cycle represents a fundamental way the magnetosphere processes and releases the energy it continuously absorbs from the silent solar wind. Fact 22. The specific colors of the aurora are beautiful fingerprints of atomic physics happening high in our atmosphere. The dominant green light, at a wavelength of 557.7 nanometers, comes from atomic oxygen. When a high-energy electron strikes an oxygen atom, it excites one of the atom's own electrons into a higher energy level. This particular excited state is metastable, meaning the electron lingers there for a relatively long time, about 3/4 of a second, before it naturally falls back down to a lower energy level, releasing the excess energy as a green photon. The red light, often seen higher up, usually at wavelengths of 630.0 and 636.4 nanometers, also comes from atomic oxygen, but from a different, even longer-lived metastable state, taking almost 2 minutes to decay. This red emission only happens at very high altitudes where the air is extremely thin, because if the excited oxygen atom collides with another particle before it has time to emit the red light, it loses the energy without radiating. Nitrogen molecules, being more abundant at lower altitudes and reacting faster, contribute the blues, around 427.8 nanometers, and purples violets often seen along the lower edges of curtains, as well as some deeper reds at higher altitudes. These nitrogen emissions happen much more quickly after excitation. The silent glow is a direct translation of quantum leaps occurring in countless individual atoms, dictated by the immutable laws of physics. Fact 23. The distinct layering of colors sometimes seen in auroral curtains, with red often appearing at the top and green or pink-purple fringes at the bottom, is a direct consequence of atmospheric density and the energy of the incoming particles. The solar wind electrons raining down have a range of energies. Higher energy electrons penetrate deeper into the atmosphere before they lose their energy through collisions, while lower energy electrons are stopped at higher altitudes. The deep red aurora occurs above 300 kilometers, where atomic oxygen is present, but the atmosphere is so thin that the long-lived excited state required for red emission isn't disrupted by collisions. The common green aurora dominates between 100 and 300 kilometers, where atomic oxygen is abundant and the density is just right for the metastable green emission to occur efficiently. Below about 100 kilometers, the atmosphere becomes denser, and collisions are more frequent. Here, the incoming electrons primarily excite nitrogen molecules, which emit light rapidly, producing the blue, purple, or pinkish-red fringes often seen along the lower border of active displays. This vertical separation of colors acts like a silent atmospheric thermometer, revealing the altitude and atmospheric composition where the different energetic collisions are taking place, painting layers of light based on density and atomic interactions. Fact 24. Earth's magnetic field is not a perfect, symmetrical dipole like a simple bar magnet. It's complex and constantly, albeit slowly, changing. Firstly, the magnetic axis is tilted by about 10 to 11 degrees relative to Earth's rotational axis, meaning the north and south magnetic poles don't coincide with the geographic poles. This tilt is why the auroral ovals are also offset from the geographic poles. Secondly, the magnetic field isn't perfectly centered within the Earth. The dipole is slightly offset from the planet's geometric center. Thirdly, the field strength varies across the globe. It's generally weaker over the South Atlantic anomaly, and stronger over areas like Siberia and northern Canada. Furthermore, the magnetic poles themselves wander over time due to the churning motions of the molten iron in the outer core. The North Magnetic Pole, for example, has been drifting noticeably faster in recent decades, moving away from Canada towards Siberia. These complexities and slow changes in the Earth's main magnetic field influence the precise location and shape of the auroral ovals over long timescales, subtly shifting the stage for the silent celestial light show. Fact 25. While Christian Birkeland laid crucial groundwork, understanding the aurora involved many scientific steps. Early spectroscopic analysis in the late 19th and early 20th centuries by scientists like Anders Angstrom was vital. By splitting the auroral light into its component wavelengths, they identified the characteristic green line at 557.7 nanometers, but couldn't initially match it to any known element under laboratory conditions, leading to speculation about a hypothetical new element called geocoronium. It wasn't until later that scientists realized it was oxygen emitting light under the very low density conditions of the upper atmosphere. The direct confirmation of the solar wind's existence and its role came only in the space age. While proposed theoretically earlier, NASA's Mariner 2 spacecraft mission to Venus in 1962 made the first direct measurements of this continuous stream of particles flowing from the Sun. Later satellite missions, flying through the magnetosphere, directly detected the energetic electrons precipitating into the atmosphere during auroral events, finally confirming the complete chain of events from the Sun to the silent lights in our sky, piecing together the puzzle over centuries of quiet observation and discovery. Fact 26. The persistent question of whether the aurora produces directly audible sounds remains largely unresolved in favor of silence, despite many anecdotal reports of crackling, swishing, or hissing noises accompanying intense displays. Given the extreme altitude, 100+ kilometer, and near vacuum conditions where the aurora occurs, it's physically implausible for sound waves generated there to travel to the ground and be heard. Sound requires a medium, and the air is far too thin at those heights. However, several potential explanations for the perceived sounds exist. One is psychoacoustic phenomena, where the visual stimulus might trigger an auditory sensation in some individuals, or sounds from other sources, like wind rustling clothes, are misinterpreted. Another possibility involves electrophonic effects. During intense geomagnetic storms, the changing magnetic fields might induce electrical effects much closer to the ground, potentially causing objects near the observer, like pine needles, hair, or even eyeglasses, to vibrate or discharge faintly, creating actual sounds very close by. While the aurora itself shines in silence, the powerful geomagnetic disturbances accompanying it might, under rare conditions, create subtle, localized noises near the Earth's surface. Fact 27. During strong auroral displays, enormous electrical currents, called auroral electrojets, flow horizontally through the ionosphere within the auroral ovals. These currents are part of a global electrical circuit, driven by the interaction of the solar wind with the magnetosphere, known as the Birkeland currents, which flow along magnetic field lines into and out of the ionosphere. The electrojets can carry millions of amperes of current, flowing primarily eastward on the evening side and westward on the morning side of the oval. These immense, high-altitude electrical flows create their own magnetic disturbances, which can be measured by ground-based magnetometers. Furthermore, these rapidly changing ionospheric currents can induce secondary electrical currents, geomagnetically induced currents, or GICs, in long-conducting networks on the ground, such as power lines, pipelines, and communication cables. These GICs are the primary mechanism by which severe space weather can disrupt our technological infrastructure, a silent, invisible electrical consequence of the beautiful lights above. Fact 28. Citizen scientists play an increasingly important role in auroral research. Dedicated aurora chasers and amateur photographers, equipped with sensitive digital cameras, often capture subtle, transient, or unusual auroral forms that might be missed by scientific instruments with narrower fields of view or lower time resolution. The discovery and characterization of strong thermal emission velocity enhancement, is a prime example. This distinct mauve ribbon of light was initially documented extensively by amateur observers in Canada, who brought it to the attention of scientists. Their photographs and observations were crucial in recognizing it as a unique phenomenon, distinct from traditional aurora, leading to dedicated scientific study using satellites and ground-based instruments. Networks of citizen observers around the world now contribute valuable data on auroral occurrence, shapes, and movements, expanding our eyes on the sky and helping to unravel the remaining quiet mysteries of these high-altitude light shows. Fact 29. Satellites orbiting Earth can be significantly affected by the same geomagnetic storms that cause intense auroras. While the lights themselves are harmless, the associated energetic particles and atmospheric changes pose risks. High-energy electrons trapped in the magnetosphere can penetrate satellite shielding, causing surface charging, leading to electrostatic discharges or sparks that can damage electronics, or deep dielectric charging, building up charge within insulating materials. Energetic protons from solar events can cause single-event upsets, bit flips, in computer memory or even permanent damage to components. Furthermore, the energy deposited in the upper atmosphere during a storm causes it to heat up and expand. This increases the atmospheric drag on satellites in low Earth orbit, causing them to lose altitude faster than expected and requiring more frequent orbital adjustments. Managing these quiet threats from space weather is a crucial aspect of satellite operations. Fact 30. Auroral tourism has become a significant travel industry in regions located beneath or near the auroral ovals. Places like Iceland, northern Norway, Sweden, Finland, Canada, Yukon, Northwest Territories, and Alaska attract visitors from around the world, especially during the winter months when the nights are long and dark. People travel great distances hoping to witness the ethereal beauty of the northern lights. This specialized tourism often involves guided tours, stays in remote lodges or glass igloos designed for aurora viewing, and photography workshops. While weather and solar activity make sightings unpredictable, the chance to experience this profound natural spectacle firsthand is a powerful draw. It connects the abstract science of solar physics and magnetospheric interactions directly back to a deeply human experience of wonder and awe in the face of nature's silent, grand celestial artistry. Fact 31. The altitude at which auroral colors are produced directly relates to the energy of the incoming particles and the density of the atmosphere. Imagine the electrons streaming down from space like a shower. The most energetic electrons have enough momentum to penetrate deeper into the atmosphere before they are stopped by collisions, reaching altitudes below 120 kilometers, about 75 miles. Down here, the atmosphere is denser, and collisions are frequent. These high-energy impacts primarily excite nitrogen molecules, causing them to rapidly emit the pinks, blues, and purples often seen along the lower edges of bright auroral arcs and curtains. Less energetic electrons don't make it as far down. They lose their energy through collisions at higher altitudes, primarily between 100 and 300 kilometers, 60 to 180 miles. This is the sweet spot for exciting atomic oxygen to produce its characteristic, relatively long-lasting green light, 557.7 nanometers, the most common auroral color. Even lower energy electrons, or those arriving during less intense events, might only interact with the very tenuous atmosphere above 300 kilometers. Here, collisions are very infrequent, allowing atomic oxygen, once excited, to remain in its very long-lived metastable state long enough to emit the deep red light, 630.0 nanometers. Thus, the vertical structure of the aurora acts as a silent spectrometer, sorting the incoming solar particles by energy and painting the sky with colors corresponding to different atmospheric layers and atomic processes, a quiet display of physics unfolding hundreds of kilometers above us. Fact 32. The auroral oval is not static, it constantly changes shape and size, depending on the level of geomagnetic activity driven by the solar wind. During quiet periods, when the solar wind is slow and its magnetic field is perhaps northward or weakly southward, the oval is typically a relatively thin ring located at high magnetic latitudes, perhaps around 70 to 75 degrees. It might be faint and confined mostly to the polar regions. However, when Earth's magnetosphere is disturbed by a gusty solar wind stream or, more dramatically, by the impact of a coronal mass ejection, CME, the oval brightens significantly and expands towards the equator. During a major geomagnetic storm, the oval can swell dramatically, pushing far south in the northern hemisphere and far north in the southern hemisphere. This expansion is a direct result of the enhanced energy input into the magnetosphere, causing more particles to be trapped and accelerated, and altering the magnetic field configuration, allowing precipitation to occur over a much wider area. Observing the size and intensity of the auroral oval provides a direct, visual gauge of the ongoing interaction between the Sun's activity and Earth's magnetic shield, a silent, luminous indicator of the current space weather conditions affecting our planet. Fact 33. The interaction creating the aurora happens in the ionosphere and thermosphere, specific layers of Earth's upper atmosphere. The thermosphere is a vast region starting around 80 to 100 kilometers and extending hundreds of kilometers upwards, characterized by extremely high temperatures due to absorption of solar radiation, but very low density. The ionosphere overlaps with the thermosphere and extends higher. It's defined not by temperature but by the presence of ions and free electrons created when solar ultraviolet and X-ray radiation strip electrons from atmospheric atoms and molecules, ionotation. The aurora occurs precisely within these layers because this is where the incoming energetic particles from the magnetosphere finally encounter enough atmospheric atoms, oxygen, and molecules, nitrogen, oxygen, to cause significant excitation through collisions. The ionosphere, being electrically charged, also plays a crucial role in conducting the enormous electrical currents, auroral electrojets, associated with auroras. So, the aurora is not just a light show. It's a visible manifestation of complex plasma physics occurring where Earth's neutral upper atmosphere meets the charged environment of space, a silent dance between solar particles and atmospheric gases in an electrically active region far above our heads. Fact 34. Auroras are often classified by their visual forms and structures, which provide clues about the underlying physical processes. Common forms include arcs, which are relatively stable, east-west aligned bands of light, often seen early in an auroral display. Bands are similar but may show more folding or structure. Patches are diffuse, cloud-like areas of light, often seen pulsating later in a substorm. Rays are vertical, beam-like structures that align with the local magnetic field lines, often appearing within arcs or bands, giving the impression of curtains. Curtains, or draperies, are folded, sheet-like structures, often exhibiting rapid movement and shimmering, representing some of the most dynamic displays. A corona forms when rays appear directly overhead, seeming to converge due to perspective effects, like looking up into a celestial crown of light. These classifications, developed through decades of quiet observation, help scientists categorize displays and relate the visible patterns to the specific ways particles are entering the atmosphere and how the magnetic field lines are guiding them, decoding the silent language written in light across the sky. Fact 35. The energy transfer from the solar wind into the magnetosphere is most efficient when the interplanetary magnetic field, IMF, carried by the solar wind has a southward component, -BZ, opposite to Earth's magnetic field direction on the day side. This condition allows for magnetic reconnect ion to occur more readily at the magnetopause, the boundary between the solar wind and Earth's magnetosphere. Reconnect ion is a process where magnetic field lines from the solar wind and Earth's field break and reconnect, creating newly configured field lines. When the IMF is southward, this reconnect ion essentially opens a doorway, peeling back Earth's magnetic field lines and allowing solar wind energy and particles to be transferred much more efficiently into the magnetosphere. These newly connected field lines are then dragged back into the magnetotail, storing more energy and ultimately leading to more frequent and intense auroral substorms when that energy is released. Conversely, when the IMF is northward, +BZ, reconnect ion happens differently, often behind the Earth at higher latitudes, and less energy is typically coupled into the system, usually resulting in quieter auroral conditions or different phenomena like theta auroras. The silent orientation of this invisible magnetic field carried by the solar wind is a key gatekeeper controlling the intensity of the lights. Fact 36. While electrons are the primary culprits for most visible auroras, protons from the solar wind also enter the magnetosphere and precipitate into the atmosphere, creating their own type of aurora, although it's often fainter and harder to see. As protons, which are hydrogen nuclei, spiral down magnetic field lines, they can capture electrons from atmospheric atoms through charge exchange, briefly becoming neutral hydrogen atoms. These energetic hydrogen atoms continue traveling downwards but are no longer guided by the magnetic field. They collide with other atmospheric particles, exciting them and causing them to emit light, typically a diffuse, weak glow often spread over a broader area than electron auroras. Because the hydrogen atoms themselves also get excited in these collisions, they emit their own characteristic light, like the hydrogen alpha line in the red part of the spectrum. But this emission is often Doppler shifted due to their high speed, making it harder to detect from the ground without specialized instruments. This proton aurora is a quieter, less conspicuous counterpart to the familiar electron-driven displays, another layer in the complex interaction. Fact 37. The aurora influences the chemistry and temperature of the upper atmosphere. The energetic particles crashing into the atmosphere not only cause excitation, leading to light emission, but also ionization, knocking electrons off atoms' molecules, and dissociation, breaking molecules apart. These processes create highly reactive chemical species, such as nitric oxide (NO), in the thermosphere and mesosphere. Nitric oxide produced during auroral events can be transported downwards and play a role in catalytic cycles that destroy ozone in the stratosphere, particularly in the polar regions during winter. Furthermore, the energy deposited by the auroral particles heats the upper atmosphere, the thermosphere. During major geomagnetic storms, this heating can be substantial, causing the thermosphere to expand significantly. This expansion increases atmospheric drag on satellites in low Earth orbit, as mentioned earlier. The aurora is therefore not just a visual phenomenon but an active driver of chemical and thermal changes in the highest reaches of our atmosphere, a silent but potent influence. Fact 38. Observing the aurora requires darkness and patience. City lights create significant light pollution that washes out all but the very brightest auroral displays. Finding a location far from urban areas with a clear, unobstructed view towards the north, in the northern hemisphere, or south, in the southern hemisphere, is crucial. The human eye also needs time to adapt to the darkness, typically 15 to 30 minutes, to become sensitive enough to perceive fainter auroras. Auroral activity waxes and wanes, so patience is key. A quiet sky might suddenly erupt into activity, or a bright display might fade quickly. The best times are usually around local magnetic midnight, which can differ slightly from clock midnight depending on your location relative to the magnetic pole. Checking short-term aurora forecasts based on real-time solar wind data can increase the chances of a successful viewing, turning the wait into a quiet anticipation under the vast night sky. Fact 39. The intensity of auroras is often measured using the KP index, a scale that quantifies geomagnetic activity based on measurements from ground-based magnetometers around the world. The scale runs from 0, very quiet, to 9, extreme geomagnetic storm. Higher KP values generally correlate with brighter, more dynamic, and more equatorward-reaching auroras. A KP of 5 or higher is considered a geomagnetic storm. Forecasts often predict the expected KP level, giving aurora watchers an indication of potential activity. For observers at mid-latitudes, like the northern US or Central Europe, a KP of 5 or 6 might bring the aurora to the northern horizon, while KP 7, 8, or 9 could result in spectacular overhead displays visible much further south. This index provides a simple, numerical language to describe the level of quiet or disturbance in Earth's magnetic field, directly linked to the visibility of the lights. Fact 40. Auroras occur within Earth's thermosphere, a layer characterized by extremely high temperatures but incredibly low density. Temperatures can reach 500 degrees Celsius to 2000 degrees Celsius or more, depending on solar activity. This extreme heat is due to the absorption of high-energy solar radiation, UV and X-rays, by the sparse gas molecules present. However, because the density is so low, billions of times less dense than air at sea level, the heat content is very small. You wouldn't feel hot if you were somehow exposed to the thermosphere, though you'd have other problems. The auroral particles deposit additional energy, further heating this layer locally. Despite the hot temperatures needed for certain red oxygen emissions, the overall environment is a near vacuum, a silent, vast, and tenuous region where the final interactions creating the aurora take place, bridging the gap between Earth's atmosphere and the cold vacuum of space. Fact 41. The beautiful, curtain-like shapes of the aurora are a direct consequence of how the energetic particles travel and where they come from. These particles, primarily electrons accelerated in the magnetotail during substorms, do not simply rain down randomly. Instead, they are guided precisely along Earth's magnetic field lines, spiraling around them like beads on an invisible wire. These paths converge as they approach the poles, funneling the particles into the high-latitude atmosphere. Furthermore, the electrons often travel in vast sheets or filaments associated with large-scale electrical currents flowing between the magnetosphere and the ionosphere. These are known as Birkeland currents, named after Christian Birkeland, who first proposed their existence. Where these sheets of current carry electrons downwards into the atmosphere, the collisions excite the gases and create the luminous curtains we see. The folds and ripples in these curtains reflect the complex structures and instabilities within these current sheets far out in space. The vertical rays within the curtains perfectly trace the direction of the local magnetic field lines, stretching upwards towards the magnetic zenith. Observing these flowing, silent shapes is like watching a map of Earth's magnetic field being illuminated from within by particles arriving from deep within the magnetosphere, a visual tracer of invisible cosmic pathways. Fact 42. The specific atomic and molecular composition of Earth's upper atmosphere is the silent canvas upon which the aurora paints its colors. Below about 100 kilometers, 60 miles, the atmosphere is dominated by molecular nitrogen, N2, and molecular oxygen, O2, similar to the air we breathe but much thinner. Above this altitude, solar ultraviolet radiation becomes intense enough to break these molecules apart. Between roughly 100 and 600 kilometers, atomic oxygen O becomes a major, and often dominant, component, alongside remaining N2. Above 600 kilometers, the lightest gases, helium and hydrogen, start to dominate. The aurora occurs primarily in the region rich in atomic oxygen and molecular nitrogen. As incoming energetic particles collide with these atoms and molecules, they transfer energy, exciting them. Each gas has a unique set of allowed energy levels, like specific notes on a musical instrument. When the excited atom or molecule relaxes back to a lower energy state, it emits a photon of light with a very specific wavelength, color, corresponding exactly to the energy difference between the levels. The prevalence of green, from atomic oxygen around 100 to 300 kilometers, red, atomic oxygen above 300 kilometers, and blue or purple pink, molecular nitrogen below 120 kilometers, directly reflects the abundance of these gases at different altitudes and the specific energy transitions favored by the particle collisions. A silent spectral signature of our upper air. Fact 43. While the aurora itself occurs in near silence far above, the idea that observers sometimes hear sounds like crackling or hissing during intense displays remains a persistent and intriguing mystery. Direct sound wave transmission from 100+ kilometer altitude is impossible. However, one plausible physical explanation involves electrophonic transduction. During extremely strong auroral events associated with major geomagnetic storms, The rapidly fluctuating geomagnetic fields can induce strong electric fields and currents not just in the ionosphere, but potentially extending much closer to the ground. These intense, low-frequency electromagnetic fluctuations could theoretically interact with objects near an observer, perhaps their hair, eyeglasses, or even natural materials like pine needles, causing them to vibrate or create small electrical discharges, corona discharges, in sync with the auroral pulsations. This would transduce the electromagnetic energy into actual sound waves locally near the observer, creating a genuine, albeit very faint, audible sensation directly linked to the auroral activity. This remains an area of active research, suggesting that while the lights themselves are silent, the powerful forces behind them might occasionally create subtle, ground-level acoustic whispers for the most attuned listeners during the most intense storms. Fact 44. Witnessing the aurora depends on more than just solar activity. Location and timing are crucial. Being underneath or near the auroral oval is paramount. This means being at high magnetic latitudes, typically between 60 and 75 degrees, is ideal. Locations like central Alaska, northern Canada, Iceland, northern Scandinavia, and Siberia are prime viewing spots. Geographic latitude alone isn't sufficient. Proximity to the magnetic pole matters most. The best time of night is generally centered around magnetic midnight, the time when the observer is geographically positioned opposite the sun relative to the magnetic pole. This is often, but not always, close to local clock midnight. The time of year also plays a role. The periods around the spring and autumn equinoxes, March, April and September, October, statistically tend to have higher geomagnetic activity and thus more frequent auroras, possibly due to the alignment of Earth's magnetic axis relative to the solar wind flow. Of course, clear, dark skies are essential. Avoiding light pollution from cities and minimizing moonlight, viewing around the new moon phase is best, significantly improves the chances of seeing fainter displays. Finally, simple weather is often the deciding factor. Even the most spectacular aurora will be hidden behind clouds. Successful aurora viewing requires aligning all these quiet celestial and terrestrial conditions. Fact 45. The South Atlantic Anomaly, SAA, is a vast region stretching from South America across the South Atlantic where Earth's magnetic field is significantly weaker than elsewhere. This weakness is due to the offset and tilt of Earth's magnetic dipole relative to its center. In the SAA, the inner Van Allen radiation belt, a zone of energetic particles trapped by the magnetic field, dips much closer to the Earth's surface than usual, down to altitudes of only a few hundred kilometers. Satellites passing through this region are exposed to higher levels of radiation, increasing the risk of electronic upsets. While not producing bright, structured auroras like those seen at the poles, the increased particle precipitation in the SAA can occasionally cause faint, diffuse atmospheric glows or airglow enhancements. These phenomena are related to the interaction of trapped radiation belt particles with the upper atmosphere, rather than directly injected solar wind particles causing polar auroras. But they represent another quiet way energetic particles interact with our atmosphere due to imperfections in our planet's magnetic shield. Fact 46. Not all auroras are bright enough to be seen with the naked eye. Subvisual auroras are light emissions occurring in the upper atmosphere through the same excitation processes, but their intensity is below the threshold of human vision. Sensitive cameras, especially those capable of long exposures or detecting specific wavelengths, can often capture these faint glows even when the sky appears dark to an observer. High-altitude red auroras, 630.0 nanometers, in particular, are often subvisual because the emission comes from a very long-lived atomic oxygen state and occurs in the extremely tenuous upper thermosphere. Diffuse, widespread glows caused by lower levels of particle precipitation might also fall below the visual threshold. These invisible light shows are still actively studied by scientists using specialized instruments like photometers and spectrographs, revealing the constant, quiet simmering of particle interaction even when the sky isn't putting on a dramatic visual performance, reminding us that the auroral process is a continuous, though variable, phenomenon. Fact 47. The intense energy deposited into the ionosphere during auroral events significantly heats the plasma, ionized gas, and neutral gas in the region, causing it to expand. This heating and the presence of energetic particles drastically alter the electrical properties of the ionosphere within the auroral oval. One major effect is increased absorption of radio waves passing through the D region, the lowest part of the ionosphere, which can cause shortwave radio blackouts in polar regions during strong events. Auroral structures can also scatter and refract radio signals, causing rapid fluctuations in signal strength and phase known as scintillation. This scintillation can severely degrade the accuracy of GPS, Global Positioning System, signals, which must travel through the ionosphere from satellites to ground receivers. The turbulent, energized ionosphere during an aurora acts like a distorting lens or a noisy filter for radio communications and navigation signals, a silent disruption caused by the very same particle bombardment that creates the beautiful lights. Fact 48. Because the charged particles causing auroras follow Earth's magnetic field lines, and these field lines connect the northern and southern hemispheres, auroras typically occur simultaneously in both polar regions. The Aurora Borealis in the north and the Aurora Australis in the south often mirror images of each other, occurring at opposite ends of the same bundle of magnetic field lines. These are known as conjugate auroras. Observing conjugate points simultaneously, for example, with ground cameras in Alaska and Antarctica, or using satellites, provides valuable information about the symmetry of particle precipitation and the structure of Earth's magnetic field. Differences in brightness or shape between conjugate auroras can indicate distortions in the magnetosphere caused by varying solar wind conditions or seasonal effects, due to the tilt of Earth's axis changing how each pole is illuminated by the Sun. They are silent twins, reflecting the magnetic connection between Earth's two polar extremities. Fact 49. Not all solar wind disturbances that trigger auroras are the same. Two main types exist: coronal mass ejections, CMEs, and high-speed streams, HSS. CMEs are vast, explosive eruptions of plasma and magnetic field from the Sun, often associated with solar flares. They travel outwards relatively slowly, taking 1 to 4 days to reach Earth, but can deliver a powerful, concentrated blow to the magnetosphere, often containing a strong southward IMF component. CMEs are typically responsible for the most intense, widespread geomagnetic storms and the most spectacular, dynamic, low-latitude auroral displays. HSS, on the other hand, originate from coronal holes, areas in the Sun's corona where the magnetic field lines open outwards, allowing solar wind to escape much faster, up to 800 kilometers per second or more. As the Sun rotates, these streams sweep across Earth periodically, like a sprinkler. HSS tend to cause less intense but more prolonged periods of moderate geomagnetic activity and auroral visibility, often lasting for several days. Understanding these two different drivers helps predict the likely duration and intensity of the resulting quiet or active auroral periods. Fact 50. While satellites provide a global view and ground-based instruments offer continuous monitoring, sounding rockets offer a unique, high-resolution snapshot directly inside an active aurora. These relatively small, suborbital rockets are launched from high-latitude ranges, like Poker Flat in Alaska or Andøya in Norway, on trajectories that take them right through auroral curtains and arcs. Carrying specialized instruments, they provide brief but incredibly detailed in situ measurements of the energy and direction of auroral electrons and ions, the electric and magnetic fields driving them, the resulting atmospheric emissions, and the plasma waves involved, all with much higher spatial and temporal resolution than orbiting satellites can achieve. These flights, often lasting only 10 to 20 minutes, require precise timing to launch into the desired auroral feature, offering a fleeting but invaluable glimpse into the microphysics occurring within the heart of the silent, dynamic lights, directly capturing the particle interactions as they happen. Fact 51. The vast majority of the light we see in the aurora comes from electrons striking the atmosphere. However, protons from the solar wind also enter the magnetosphere and rain down. When these energetic protons collide with atmospheric gases, they can steal an electron, becoming neutral hydrogen atoms for a brief moment. These fast-moving hydrogen atoms are no longer constrained by the magnetic field and continue traveling downwards, colliding with other atmospheric particles. These collisions excite the background gases, oxygen and nitrogen, causing them to emit light, creating a very faint, diffuse glow known as proton aurora. The excited hydrogen atoms themselves also emit light, particularly the red hydrogen alpha line, but because they are moving so fast towards us, this light is often Doppler shifted to shorter wavelengths, making it difficult to observe easily from the ground without specialized filters. Proton aurora typically occurs slightly equatorward of the main electron aurora oval and appears as a broad, weak glow, lacking the sharp structures of curtains and rays. It is a much quieter, more subdued counterpart to the dramatic displays driven by electrons, a gentle hydrogen whisper compared to the vibrant electron song filling the high atmosphere during a display. Fact 52. The shape of Earth's magnetic field is crucial for creating the auroral ovals. Imagine the field lines emerging from near the south magnetic pole, looping far out into space, and re-entering near the north magnetic pole. In the vast region called the magnetotail, stretching away from the Sun, these field lines become highly elongated. The particles that cause the aurora, electrons and protons trapped from the solar wind or originating from Earth's ionosphere, are stored in this magnetotail region, specifically in an area called the plasma sheet. When processes like magnetic reconnect ion occur, these particles are accelerated back towards Earth along the magnetic field lines. Because the field lines connecting to the distant plasma sheet converge back to Earth in specific high-latitude regions, the particles are naturally funneled into these areas. The auroral ovals represent the footprints of this particle precipitation, tracing the regions where the field lines originating from the dynamic heart of the magnetosphere connect down to the ionosphere. The oval shape reflects the structure of this magnetic connection, a luminous ring showing where the energy stored far out in the magnetotail silently pours back into our upper atmosphere, following invisible magnetic pathways. Fact 53. The aurora is intrinsically linked to electrical currents flowing between space and Earth's upper atmosphere, known as Birkeland currents. These currents flow along Earth's magnetic field lines, carrying millions of amperes. They flow down into the ionosphere on the dawn side of the auroral oval and up out of the ionosphere on the dusk side, closing through horizontal currents, the auroral electrojets, within the ionosphere itself. These downward Birkeland currents are often carried primarily by energetic electrons accelerated towards Earth. When these electrons hit the atmosphere, they create the bright auroral displays. Therefore, the most visible auroral structures, like bright arcs and curtains, often mark the regions where these powerful, invisible electrical currents are connecting the magnetosphere to the ionosphere. The aurora, in this sense, is like the glowing filament in a vast cosmic circuit, illuminated where the current flows most intensely, a silent visualization of enormous electrical power transfer. Fact 54. While we typically think of aurora in terms of visible light, the particle collisions also generate emissions across other parts of the electromagnetic spectrum. Auroral processes produce significant ultraviolet, UV, emissions, which can be observed by satellites above the atmosphere, as Earth's atmosphere blocks most UV from reaching the ground. These UV auroras are particularly useful for getting a global view of the auroral oval's extent and intensity, even on the planet's dayside where visible aurora is washed out by sunlight. Infrared, IR, emissions are also generated, primarily from the vibrational and rotational excitation of molecules like nitric oxide, which is produced during auroral activity. Studying these IR emissions provides information about the energy deposition and chemical changes occurring in the upper atmosphere. Furthermore, as mentioned, X-rays can be produced when very high-energy electrons, sometimes called killer electrons, precipitate into the atmosphere. These are usually observed only during intense geomagnetic storms using balloons or satellites. The aurora is a multi-wavelength phenomenon, a silent symphony playing across different energy levels, though our eyes only perceive the visible notes. Fact 55. The concept of magnetic reconnect ion is fundamental to understanding how energy from the solar wind gets into the magnetosphere and powers auroras. Magnetic field lines originating from different sources, like the Sun's IMF and Earth's magnetic field, can essentially break and reconnect when they are forced together under specific conditions, usually when they are pointing in opposite directions. This process occurs both at the dayside magnetopores, allowing solar wind plasma to enter, and in the magnetotail, releasing stored energy. Reconnect ion converts stored magnetic energy into kinetic energy, accelerating particles, and thermal energy, heating plasma. The reconnect ion event in the magnetotail, snapping the stretched field lines back towards Earth, acts like a slingshot, propelling electrons towards the poles at high speeds. This sudden release and particle acceleration is the direct trigger for auroral substorm expansion phases, the dramatic brightening and rapid movement of the aurora across the sky. It's a fundamental process of magnetic reconfiguration, a quiet snapping of invisible field lines that unleashes a cascade of visible light. Fact 56. Oxygen plays a dual role in auroral colors, producing both the most common green and the high-altitude red. This difference arises from the distinct ways oxygen atoms can be excited and how long they stay excited before emitting light. The transition that produces the green light, 557.7 nanometers, involves an electron moving from one specific excited energy level, the to the power of 1s state, down to another, the to the power of 1d state. This is a forbidden transition in quantum mechanics, meaning it doesn't happen easily or quickly, taking about 0.75 seconds on average. The transition producing the main red light, 630.0 nanometers, involves an electron moving from that intermediate excited level, to the power of 1d, down to the ground state, cubed p. This transition is even more forbidden, taking an average of about 110 seconds, almost 2 minutes. At the altitudes where green aurora forms, 100 to 300 kilometers, the atmosphere is dense enough that collisions happen frequently, but usually not faster than the 0.75 seconds needed for green emission. However, collisions are frequent enough to often knock the oxygen atom out of the to the power of 1d state before it has the 110 seconds needed to emit red light, a process called collisional quenching. Only at very high altitudes, above 300 kilometers, where the air is extremely thin and collisions are rare, do the oxygen atoms have enough undisturbed time to complete the slow decay and emit the red photons. This delicate timing, governed by quantum rules and atmospheric density, paints the silent sky with distinct layers of color. Fact 57. The Sun's activity, and therefore auroral activity, follows a roughly 11-year cycle, known as the solar cycle. This cycle is driven by changes in the Sun's magnetic field, which flips its polarity, north becomes south and vice versa, approximately every 11 years. The period around solar minimum is characterized by fewer sunspots, solar flares, and CMEs, leading to generally weaker and less frequent auroral displays, often dominated by effects from high-speed streams from coronal holes. Conversely, the period around solar maximum sees a peak in sunspots, flares, and CMEs. This heightened activity results in more frequent and intense geomagnetic storms, leading to brighter, more dynamic auroras that often reach lower latitudes. We are currently in solar cycle 25, heading towards its predicted maximum around 2024 to 2025. Tracking this cycle helps predict the overall likelihood of seeing strong auroras over the course of years, a slow, quiet rhythm governing the Sun's temper and its effect on our polar lights. Fact 58. While Earth's global magnetic field shields us, some magnetic field lines originating near the poles extend directly out into the solar wind, forming the polar cusp regions. These cusp regions act like funnels where solar wind plasma can have more direct access to Earth's upper atmosphere compared to other areas. Particle precipitation through the cusps creates day-side auroras, which occur, as the name suggests, on the sunlit side of the Earth. These are often fainter and less structured than the bright night-side auroras powered by magnetotail dynamics, but they can appear as diffuse glows or arcs, sometimes with a predominantly red color, due to excitation occurring at higher altitudes. Observing these day-side auroras provides direct information about the immediate interaction between the solar wind and the magnetosphere at the magnetopore's boundary, a quiet indicator of the solar wind's direct entry point. Fact 59. Auroral displays can sometimes generate infrasound, sound waves with frequencies below the range of human hearing, below 20 Hz. These low-frequency sound waves can travel long distances through the atmosphere. It's thought that the rapid heating and expansion of the atmosphere caused by the intense energy deposition during bright, fast-moving auroras, as well as the movement of the large electrical currents, electrojets, could generate these pressure waves high in the atmosphere. Sensitive microbarometers on the ground can sometimes detect these infrasound signals arriving from the direction of an active aurora, hours after the display occurred, due to the slow speed of sound compared to light. While we cannot hear it directly, the aurora might be communicating through these silent, ultra-low frequency vibrations traveling down through the atmosphere, a quiet rumble accompanying the visual spectacle. Fact 60. The energy that ultimately powers the aurora originates from the Sun's nuclear fusion. Deep within the Sun's core, hydrogen atoms fuse together to form helium, releasing tremendous amounts of energy in the process. This energy travels outwards, eventually heating the Sun's outer layers, the corona, to millions of degrees. It is this extreme heat that drives the expansion of the coronal plasma outwards, forming the solar wind. The kinetic energy of the particles in the solar wind, along with the energy stored in the magnetic fields carried within it, is the raw power source. Earth's magnetosphere captures a tiny fraction of this energy flow, perhaps less than 0.1%, and then processes and redirects it, ultimately funneling it into the polar regions where it is dissipated through collisions with atmospheric gases, producing the light we see. The aurora is therefore a distant, transformed, and beautifully visible manifestation of the silent, immense nuclear furnace burning at the heart of our solar system, connecting us directly to the star that gives us life. Fact 61. The light emission in the aurora isn't instantaneous for all colors, reflecting the different ways atoms and molecules release their absorbed energy. Some emissions happen almost immediately after a particle collision, creating what's called prompt emission. This is typical for many of the transitions in nitrogen molecules, contributing to the fast-moving, rapidly changing features like the bright lower edges of curtains and flickering rays often seen in blues and purples. These emissions occur within fractions of a second after the nitrogen molecule is excited. Other emissions, however, involve metastable states, as we saw with oxygen. An atom or molecule is boosted into an excited energy level, but the quantum rules governing its return to a lower state make that transition slow or forbidden. The electron lingers in the higher state for a relatively long time before it can finally release its energy as a photon. The common green light from oxygen is a prime example, with its average delay of about 3/4 of a second. The high-altitude red light from oxygen is even more delayed, taking nearly 2 minutes on average. This difference in timing contributes to the appearance of the aurora. The prompt emissions from nitrogen can respond almost instantly to changes in the incoming particle flux, creating sharp, fast features, while the delayed emissions from oxygen, especially the red, create slower, more diffuse, and often longer-lasting glows. It's a silent testament to the different quantum timetables governing atomic relaxation in the upper atmosphere. Fact 62. Earth is surrounded by belts of trapped high-energy particles known as the Van Allen radiation belts. These belts, primarily containing energetic protons and electrons, are held in place by Earth's magnetic field, forming two main donut-shaped regions around the planet: an inner belt, mostly protons, and an outer belt, mostly electrons. While the particles causing the main auroral displays are typically injected more directly from the magnetotail during substorms, the outer radiation belt does play a role. During large geomagnetic storms, the outer belt can become significantly energized and its particles can be both accelerated to higher energies and scattered down into the atmosphere, contributing to auroral precipitation, particularly the diffuse aurora that covers large areas. Furthermore, phenomena like pulsating auroras are thought to be caused by waves within the magnetosphere interacting with trapped electrons near the outer radiation belt, periodically scattering them into the lost cone, the range of trajectories that leads them down into the atmosphere. The radiation belts represent a vast reservoir of energetic particles surrounding Earth, a quieter but potentially potent contributor to the processes that ultimately illuminate our polar skies, intricately linked to the overall dynamics of the magnetosphere. Fact 63. The precipitation of energetic particles during an aurora deposits a significant amount of energy into the upper atmosphere, primarily as heat. While the light itself is cold, the collisions transferring kinetic energy from solar particles to atmospheric gases cause substantial heating of the thermosphere and ionosphere within the auroral regions. During a major geomagnetic storm, this energy input can be enormous, rivaling the energy absorbed from solar UV radiation. This intense heating causes the upper atmosphere to expand significantly, increasing its density at higher altitudes. This expansion has practical consequences, most notably increasing the atmospheric drag on satellites operating in low Earth orbit (LEO), typically below about 1,000 kilometers altitude. Increased drag forces satellites to lose altitude more quickly, requiring more frequent orbital boosts, using precious fuel, to maintain their position. Predicting this atmospheric expansion driven by auroral energy deposition is a key aspect of space weather forecasting for satellite operators. The silent lights, therefore, are associated with an invisible but powerful heating effect that actively alters the density and extent of Earth's outermost atmospheric layers, reaching out to influence objects orbiting far above the ground. Fact 64. Determining the altitude of the aurora was a significant scientific challenge for centuries. Early observers could only guess, with estimates ranging wildly from just a few miles up to hundreds or even thousands. A breakthrough came with the application of triangulation, similar to how surveyors measure the distance to remote objects. By having two observers simultaneously view and photograph the same auroral feature, like the lower edge of an arc, from two different locations separated by a known baseline distance, tens or hundreds of kilometers apart, scientists could measure the slight difference in the apparent position of the aurora against the background stars, parallax. Using geometry, they could then calculate the height of the feature. Pioneering work using this photographic parallax method was done by Karlströmer in Norway in the early 20th century. His extensive campaigns, involving numerous observation stations connected by telephone, systematically measured thousands of auroral heights, definitively establishing that the aurora typically occurs between 100 and 400 kilometers altitude, with occasional reds reaching much higher. This quiet, meticulous geometric measurement finally placed the ethereal lights firmly within the upper reaches of Earth's atmosphere. Fact 65. The ionosphere, the electrically charged layer of the upper atmosphere created by solar radiation, acts as the conductor for the massive electrical currents associated with the aurora. The Birkeland currents flow along magnetic field lines down into the ionosphere in some regions of the auroral oval and up out of it in others. To complete the circuit, these vertical currents must connect through horizontal currents flowing within the ionosphere itself. These horizontal currents are the auroral electrojets. Because the ionosphere is only partially ionized, containing both charged particles and neutral atoms or molecules, it acts like a resistor. As the powerful electrojets flow through this resistive medium, they dissipate energy through collisions, significantly heating the ionosphere, a process called Joule heating. This heating contributes to the thermospheric expansion and also drives strong ionospheric winds. Furthermore, the energetic electrons carrying the downward Birkeland currents create additional ionization as they collide with atmospheric gases, enhancing the conductivity of the ionosphere locally within the auroral arcs and curtains, facilitating the flow of the very currents that cause them. The ionosphere is thus not just the screen upon which the aurora is projected, but an active electrical component in the vast, silent magnetosphere ionosphere circuit. Fact 66. While green, red, blue, and violet are the dominant colors, the auroral spectrum contains a multitude of other, often fainter, emission lines and bands across the visible and invisible wavelengths. These emissions come from various excited states of atomic oxygen O molecular nitrogen, N2, ionized molecular nitrogen, N2+, ionized atomic oxygen, O+, and even trace constituents like hydrogen, from proton aurora, and sodium. Each spectral line corresponds to a specific quantum leap, a transition between defined energy levels in these atoms and molecules. Studying these weaker emissions with spectrographs provides detailed diagnostic information about the composition of the atmosphere, the energy distribution of the incoming particles, the temperatures, and the chemical reactions occurring during an auroral display. For instance, certain ratios of nitrogen bands can be used to estimate the characteristic energy of the precipitating electrons. This detailed spectral fingerprint, mostly invisible to our eyes, allows scientists to read the fine print of the physical processes unfolding in the silent, luminous plasma far above. Fact 67. It's important to distinguish the aurora from another faint, natural light phenomenon called airglow. Airglow is a very weak emission of light by a planetary atmosphere that is always present, day and night, across the entire sky, not just in the polar regions. It's caused by various chemical reactions and processes in the upper atmosphere initiated by solar radiation, photodissociation, photoionization, recombination. For example, oxygen atoms recombining after being split apart by sunlight during the day can emit a faint green glow throughout the night. Other airglow emissions occur in the red, yellow, from sodium, and infrared. Airglow is typically much fainter and more uniform than the aurora, lacking its discrete structures and dynamic movements. While both involve light emission from the upper atmosphere, airglow is a result of solar radiation chemistry, while aurora is caused by the direct impact of energetic particles guided by the magnetic field. Airglow is the atmosphere's constant, quiet background hum, whereas aurora is a more localized, dynamic response to incoming solar energy channeled by the magnetosphere. Fact 68. Because Earth's magnetic field lines connect the northern and southern hemispheres, the precipitation of particles that causes the Aurora Borealis simultaneously triggers the Aurora Australis at the magnetically conjugate point in the opposite hemisphere. These two displays are often remarkably similar in shape and intensity, mirroring each other across the globe. For instance, an auroral arc seen over Alaska might have a nearly identical counterpart appearing at the same time over the Antarctic region magnetically linked to it. Satellites equipped with auroral imagers have captured stunning simultaneous views of both ovals brightening and expanding during substorms, confirming this magnetic conjugacy. Studying slight differences between the two hemispheres can provide insights into asymmetries in the magnetosphere or differences in atmospheric conditions. This silent, synchronized dance of light at both ends of the planet beautifully illustrates the global reach and structure of Earth's magnetic field. Fact 69. There has been long-standing speculation and research into potential links between solar activity and associated auroral activity and Earth's weather and climate, but the connections remain complex and often controversial. Proposed mechanisms are generally subtle. For example, energetic particles precipitating during auroras, or cosmic rays modulated by solar activity, could potentially influence upper atmospheric chemistry, like ozone levels, or even cloud formation processes lower down. Changes in the Sun's total energy output, irradiance, over the solar cycle are very small, around 0.1%, but could have long-term effects. Some studies have suggested correlations between the 11-year solar cycle or longer-term solar variations and regional weather patterns, like storm tracks or temperature anomalies, but establishing clear cause and effect relationships distinct from natural climate variability is challenging. While the Sun is undoubtedly the primary driver of Earth's climate system, the specific influence of auroral-level geomagnetic activity on tropospheric weather remains an area of active investigation, a search for quiet, high-altitude influences on our daily conditions. Fact 70. Beyond the science, witnessing a powerful auroral display is often described as a profound, almost spiritual experience. The sheer scale, the silent, graceful movement, and the ethereal colors dancing across the vastness of the night sky can evoke feelings of awe, wonder, and insignificance. For many cultures living under the auroral oval, the lights were deeply woven into their cosmology and spiritual beliefs. Even today, for tourists and locals alike, observing the aurora is often a deeply moving encounter with the natural world on a cosmic scale. It connects the observer directly to the invisible forces of the Sun and Earth, reminding us of the immense and beautiful universe we inhabit. The silence of the display often enhances its impact, allowing for quiet contemplation and a sense of connection to something ancient and powerful, a truly unforgettable spectacle of nature's artistry. Fact 71. Observing the aurora from space offers a completely different and breathtaking perspective. Astronauts aboard the International Space Station, ISS, orbiting at about 400 kilometers, 250 miles, altitude, often fly directly over or even through the upper reaches of auroral displays. From their vantage point, they can look down upon the vast, glowing curtains and ovals stretching across hundreds or thousands of kilometers of the polar regions. They witness the aurora not as an overhead spectacle against a starry sky, but as a luminous layer draped over the limb of the Earth, a vibrant green and sometimes red glow sandwiched between the planet's dark surface and the blackness of space. They can see the immense scale and dynamic movement in a way impossible from the ground, watching substorms unfold across continents. Satellites equipped with specialized auroral imagers, often operating in ultraviolet light to see the aurora even on the dayside, provide continuous global monitoring of the auroral ovals, tracking their size, brightness, and location in response to changing space weather conditions. This space-based view complements ground observations, giving scientists a complete picture of how the Sun's activity quietly paints Earth's upper atmosphere with light on a planetary scale. Fact 72. Auroras are broadly categorized into two main types based on their appearance and the nature of the particle precipitation: discrete aurora and diffuse aurora. Discrete auroras are the bright, structured forms we often associate with the northern lights, the distinct arcs, bands, rays, and curtains with relatively sharp edges. These are caused by electrons that have been accelerated to high energies, typically several kiloelectronvolts, keV, in specific regions of the magnetosphere, often associated with the upward Birkeland currents or processes during substorms. These accelerated electrons arrive in relatively narrow beams or sheets, creating localized, intense light emissions. In contrast, diffuse aurora appears as a much fainter, more widespread, and generally featureless glow covering large areas of the sky within or equator ward of the main auroral oval. It is caused by lower energy electrons, typically less than 1 keV, precipitating over a broader region, often scattered from the central plasma sheet in the magnetotail. While less spectacular visually, the diffuse aurora actually deposits a significant, and sometimes dominant, amount of the total energy into the upper atmosphere during a geomagnetic disturbance. The interplay between these bright, structured discrete forms and the underlying faint, widespread diffuse glow paints the full picture of the quiet and active energy release into our polar skies. Fact 73. The interaction between the energetic auroral electrons and the upper atmosphere generates X-rays, particularly during intense geomagnetic storms. While most auroral electrons have energies in the range of a few keV, sufficient to cause visible light emissions, during strong events, electrons can be accelerated to much higher energies, tens or even hundreds of keV. When these very high energy, relativistic or killer, electrons penetrate deeper into the atmosphere, down to altitudes around 60 to 80 kilometers, they collide violently with air molecules. This interaction produces Bremsstrahlung X-rays, literally braking radiation, which occur when the fast-moving electrons are suddenly decelerated by the electric fields of the atmospheric nuclei. These X-rays cannot be observed from the ground as they are absorbed by the lower atmosphere. However, they can be detected by instruments on high-altitude balloons or satellites. Studying these auroral X-rays provides crucial information about the most energetic particle acceleration processes occurring deep within the magnetosphere during major storms, revealing a more energetic, invisible layer to the silent light show far above. Fact 74. The Auroral Electrojet Index, AE Index, is another important measure of global auroral activity, specifically quantifying the strength of the electrical currents, electrojets, flowing in the ionosphere within the auroral ovals. It is derived from magnetic field measurements taken by a network of ground-based magnetometers located at high latitudes around the northern hemisphere. The index essentially measures the maximum range of magnetic disturbance caused by the electrojets at any given time. Large values of the AE index indicate strong electrojet currents, which are directly associated with intense particle precipitation and bright, widespread auroral displays. Unlike the KP index, which is a quasi-logarithmic scale representing general geomagnetic activity over 3-hour intervals, the AE index provides a more direct, physical measure of auroral zone current intensity, often with much higher time resolution, minutes. Scientists use the AE index to track the timing and intensity of auroral substorms and quantify the amount of energy being dissipated in the ionosphere, providing a numerical voice to the silent electrical drama unfolding overhead. Fact 74. The Auroral Electrojet Index, AE Index, is another important measure of global auroral activity, specifically quantifying the strength of the electrical currents, electrojets, flowing in the ionosphere within the auroral ovals. It is derived from magnetic field measurements taken by a network of ground-based magnetometers located at high latitudes around the northern hemisphere. The index essentially measures the maximum range of magnetic disturbance caused by the electrojets at any given time. Large values of the AE index indicate strong electrojet currents, which are directly associated with intense particle precipitation and bright, widespread auroral displays. Unlike the KP index, which is a quasi-logarithmic scale representing general geomagnetic activity over 3-hour intervals, the AE index provides a more direct, physical measure of auroral zone current intensity, often with much higher time resolution, minutes. Scientists use the AE index to track the timing and intensity of auroral substorms and quantify the amount of energy being dissipated in the ionosphere, providing a numerical voice to the silent electrical drama unfolding overhead. Fact 75. The chemical consequences of auroral particle precipitation include the significant production of nitric oxide, NO, and other reactive nitrogen species, NOx, in the thermosphere and upper mesosphere, roughly 80 to 150 kilometers altitude. Energetic electrons colliding with the abundant molecular nitrogen, N2, can break the strong N2 bond, dissociation, or ionize the molecule. These nitrogen atoms and ions then rapidly react with molecular oxygen, O2, to form NO. During major auroral events, the production of NO in the polar regions can increase dramatically. Because NO has a relatively long chemical lifetime, especially during the polar winter darkness, it can persist and be transported downwards by atmospheric circulation into the stratosphere, below 50 kilometers. Once in the stratosphere, NO acts as a catalyst in chemical cycles that destroy ozone, O3. Therefore, intense auroral activity, driven by solar storms, can lead to temporary but significant depletion of the protective ozone layer in the polar regions, providing a tangible link between space weather and the chemistry of Earth's middle atmosphere, a quiet chain reaction connecting the aurora to stratospheric composition. Fact 76. Early scientific investigations into the aurora, before the full picture involving the Sun and magnetosphere emerged, involved many notable figures. Anders Celsius, famous for his temperature scale, along with his colleague Olof Hjorth in Sweden in the 1740s, observed that intense auroral displays were often accompanied by deflections of compass needles, providing early evidence for a link between the aurora and geomagnetism. Around the same time, French scientist Jean-Jacques d'Ortus de Mairan published a comprehensive treatise on the aurora, speculating, incorrectly, but presciently, that it might be caused by solar material interacting with Earth's atmosphere. Later, in the 19th century, scientists like Elias Loomis meticulously mapped the geographical distribution of auroral sightings, establishing the concept of the auroral zone as a ring around the magnetic pole. These early, systematic observations and correlations, though lacking the full physical explanation, laid the crucial groundwork for later breakthroughs by scientists like Birkeland and those of the space age, slowly building our understanding of the silent lights through careful, quiet observation and deduction. Fact 77. Viewing the aurora from space provides astronauts with a unique perspective unavailable from the ground. Orbiting above most of the atmosphere, they see the auroral emissions as distinct layers of light against the curve of the Earth. The most common green layer often appears brightest at its lower edge, around 100 to 120 kilometers altitude, fading upwards. Higher above, the fainter red emissions can sometimes be seen, extending up to the orbital altitude of the ISS, around 400 kilometers, or even beyond. Astronauts have described flying directly through these tenuous red glows. Because they are above the denser parts of the atmosphere, the sky around them remains black, making the aurora appear as vibrant, glowing ribbons and curtains draped over the planet's limb. They can also observe the vast geographical extent of the displays, sometimes seeing the entire oval stretching across continents, and witness the dynamic movements and pulsations on a grand scale. It's a silent, privileged view of the interaction between space and Earth's atmosphere, seen from within the phenomenon itself. Fact 78. On nights with particularly bright and widespread auroras, especially in areas with snow cover, the light from the aurora can be intense enough to visibly illuminate the landscape. Observers in remote, dark locations have reported being able to see their surroundings, read large print, or notice shadows cast by the brighter auroral forms. While the aurora is a high-altitude phenomenon, its total integrated light output during a major storm can be substantial. The predominantly green light, to which human eyes are quite sensitive, reflects efficiently off snow-covered ground, creating an eerie, silent, and often gently pulsating illumination quite distinct from moonlight. This ability of the aurora to cast a visible glow upon the Earth adds to its mysterious and powerful presence, turning the night landscape into a softly lit stage for the celestial dance occurring far overhead, a quiet light bathing the world below. Fact 79. The generation of Earth's magnetic field deep within the planet's outer core is what makes the aurora possible. This field originates from the geodynamo process, driven by convection currents in the molten iron-nickel alloy of the outer core. As the hot, electrically conducting fluid rises, cools, and sinks, influenced by the Earth's rotation, Coriolis effect, it generates vast electrical currents. These currents, in turn, produce the planet's global magnetic field, which extends far out into space to form the magnetosphere. Without this internal dynamo creating our protective magnetic shield, the solar wind would directly impact Earth's atmosphere, likely stripping it away over geological time and bombarding the surface with deadly radiation. The aurora is, therefore, a beautiful side effect of the same deep, internal process that makes Earth habitable. The silent churning of molten metal thousands of kilometers beneath our feet creates the invisible shield that interacts with the sun's outflow to paint the polar skies with light. Fact 80. In essence, the aurora requires three key ingredients. First, a source of energetic charged particles, primarily electrons and protons originating from the sun and carried by the solar wind or trapped within the magnetosphere. Second, a planetary magnetic field strong enough to capture these particles and funnel them towards the polar regions. And third, an atmosphere containing gases, like oxygen and nitrogen, that can be excited by collisions with these particles and subsequently emit light. The interplay between these three components, the solar input, the planetary shield and funnel, and the atmospheric canvas, determines the occurrence, location, intensity, color, and shape of the auroral display. Variations in any of these ingredients, such as changes in solar wind speed or density, the orientation of the interplanetary magnetic field, or the composition of the upper atmosphere, will modulate the resulting silent light show. The aurora is the beautiful, visible outcome of this fundamental celestial recipe. Fact 81. Beyond the main auroral oval driven by particles from the magnetotail, another, often distinct and fainter, type of high-altitude glow can occur at lower latitudes during major geomagnetic storms. These are known as stable auroral red (SAR) arcs. Unlike the dynamic, curtain-like structures of typical auroras caused by direct particle precipitation, SAR arcs appear as broad, persistent, and almost exclusively deep red bands stretching across the sky, often visible from mid-latitudes far equatorward of the main oval. They are generated by a different mechanism. During large storms, energy is injected into Earth's ring current, a donut-shaped region of energetic ions and electrons trapped in the inner magnetosphere. This energy heats the thermal electrons in the ionosphere and plasmasphere, the cold plasma surrounding Earth. These hot electrons then collide with atomic oxygen at very high altitudes, around 400 kilometers and above, exciting them to produce the characteristic deep red, 630.0 nanometers, emission. Because the energy source is the relatively stable ring current heat flow rather than bursts of precipitating particles, SAR arcs tend to be long-lasting and lack the intricate structures and rapid movements of conventional auroras. They represent a quieter, slower release of stored magnetospheric energy into the high atmosphere, painting a gentle, persistent red blush far south of the main polar dance. Fact 82. The intricate motions observed within active auroral displays, such as the swirling, folding curtains and rapidly moving rays, directly reflect the complex dynamics of plasma instabilities and electric fields occurring far out in the magnetosphere and closer in along the magnetic field lines connecting to the ionosphere. For instance, the rapid east-west drift of auroral forms is related to large-scale electric fields within the magnetosphere that cause plasma to circulate. Smaller-scale movements, like the shimmering or flaming motions sometimes seen, might be caused by various plasma waves, like alpha waves, propagating along magnetic field lines, modulating the flow or energy of the precipitating electrons. The folding and curling of auroral curtains can be linked to instabilities, like the Kelvin-Helmholtz instability, similar to wind creating waves on water, occurring at the boundaries of plasma flows in the magnetosphere. These visible motions are essentially tracing the invisible turbulence and wave activity in the space plasma environment surrounding Earth, projected down onto the atmospheric screen. Watching the aurora's silent, fluid dance is like watching the weather patterns of space itself, made luminous for our eyes, revealing the complex ebb and flow of energy and particles hundreds of thousands of kilometers away. Fact 83. The interaction of auroral electrons with the ionosphere generates intense radio emissions known as auroral kilometric radiation, AKR. This powerful radio noise occurs at frequencies between about 50 and 500 kHz, KHZ, corresponding to wavelengths of several kilometers, hence kilometric. AKR is generated primarily by electrons spiraling rapidly around magnetic field lines in regions where plasma density is low, typically at altitudes of a few thousand kilometers above the main auroral display, within regions called auroral acceleration regions or cavities. The process involves electrons interacting collectively with plasma waves in a way that amplifies radio emissions at specific frequencies related to the local electron gyro frequency, the rate at which electrons spiral around the magnetic field. AKR is beamed outwards, away from Earth, and cannot be detected on the ground because the ionosphere blocks radio waves below about 10 MHz. However, it is readily detected by spacecraft orbiting above the ionosphere and is one of the strongest natural radio signals originating from Earth's vicinity, sometimes even exceeding the radio output of Jupiter. This intense, silent radio shout is another invisible byproduct of the same particle acceleration processes that create the visible aurora below. Fact 84. The acceleration of the electrons that cause the most brilliant auroras is thought to occur relatively close to Earth, at altitudes ranging from about 1,000 to 10,000 kilometers, roughly 600 to 6,000 miles, above the polar regions. Electrons stored in the magnetotail's plasma sheet generally have modest energies. To create the bright, structured discrete auroras, they need to be accelerated significantly as they travel towards Earth. This acceleration is believed to happen within specific regions along the magnetic field lines where strong parallel electric fields aligned with the magnetic field, can develop. These fields can arise due to complex interactions involving the Birkeland currents flowing between the magnetosphere and ionosphere, plasma instabilities, and the formation of low-density cavities along the field lines. Electrons passing through these regions are accelerated downwards by the electric potential drop, gaining the several keV of energy needed to penetrate the atmosphere and efficiently excite oxygen and nitrogen. The existence of these acceleration regions is inferred from satellite measurements and helps explain the discrete, sheet-like nature of bright auroral curtains. They trace the regions where this potent, invisible electrical acceleration is silently taking place far above the visible display. Fact 85. Human visual perception plays a role in how we experience the aurora, especially regarding color. Our eyes have two main types of photoreceptor cells, rods and cones. Cones are responsible for color vision but require relatively bright light to function well. Rods are much more sensitive to low light levels but are essentially colorblind, perceiving the world in shades of gray. Faint auroras often appear whitish or grayish to the naked eye because the light intensity is only sufficient to stimulate the highly sensitive rod cells. Only when the aurora becomes brighter do the cone cells begin to activate, allowing us to perceive the distinct colors, with green usually being the first to become apparent as our eyes are most sensitive to this wavelength. Very bright displays might reveal reds, blues, and purples. Cameras, especially with long exposures, are much better at capturing the full range of colors present, often revealing vibrant hues that were too faint for the human eye to discern directly. This difference between photographic evidence and direct visual experience highlights the quiet limitations and adaptations of our own sensory system when viewing these ethereal, low-light phenomena. Fact 86. The duration of auroral displays is highly variable. A faint, quiet arc might hang silently in the sky for hours with little change. A diffuse glow might persist throughout much of the night during periods of elevated but steady solar wind activity. However, the most dynamic phase of an auroral substorm, the expansion phase, characterized by rapid brightening, poleward movement, and formation of active curtains and rays, is typically much shorter, often lasting only 10 to 30 minutes. Following this explosive burst, the aurora usually enters a recovery phase, which can last for an hour or two, often featuring more patchy, pulsating forms or slowly fading arcs as the magnetosphere gradually returns to a quieter state. The overall period of enhanced auroral activity associated with a high-speed stream might last for several days, but the truly spectacular, fast-moving displays often occur in these relatively brief, intense bursts related to energy release from the magnetotail. Witnessing the peak of a substorm requires not only being in the right place but also catching that specific, fleeting window of intense activity, a brief, silent crescendo in the night's light show. Fact 87. Variations in the density and composition of the upper atmosphere, influenced by factors like solar activity, season, and even weather patterns lower down, can subtly affect the appearance and altitude of the aurora. For example, increased solar UV radiation during solar maximum heats and expands the thermosphere, lifting the atmospheric gases to higher altitudes. This might slightly raise the average height of auroral emissions. Seasonal changes also occur. The composition and density at a given altitude over the winter pole, in continuous darkness, can differ from the summer pole, in continuous sunlight. Atmospheric waves and tides, propagating upwards from the lower atmosphere, can create temporary density fluctuations in the thermosphere. These variations can influence how far incoming auroral particles penetrate before causing excitation, potentially affecting the brightness, the precise altitude of the lower border of arcs, and possibly even the efficiency of certain color emissions. The atmosphere is not a static canvas. Its quiet, ongoing changes add another layer of variability to the auroral display. Fact 88. While the main auroral ovals are the primary sites of aurora driven by particles from the plasma sheet and magnetotail, auroral emissions can sometimes occur even deeper within the polar cap, the region poleward of the main oval. These features, often appearing as faint, sun-aligned arcs stretching across the dark polar cap, are known as polar cap arcs or theta auroras, when they connect across the oval. They typically occur during periods when the interplanetary magnetic field, IMF, has a strong northward, positive BZ, component. Under these conditions, magnetic reconnection can happen differently, not just on the dayside magnetopores or in the tail, but possibly poleward of the cusps, allowing plasma, potentially originating more directly from the solar wind or the magnetosheath, to enter the magnetosphere over the lobes of the magnetotail and precipitate into the polar cap region. These arcs are usually much fainter and less dynamic than the main oval auroras and represent a different mode of interaction between the solar wind and the magnetosphere under specific IMF conditions, a quiet glow over the highest latitudes. Fact 89. Scientists have occasionally created artificial auroras through experiments involving electron beams. In several sounding rocket and satellite experiments, like the Charge 2 rocket or early space shuttle missions, electron accelerators were used to fire beams of electrons downwards along Earth's magnetic field lines into the upper atmosphere. These beams, mimicking the natural influx of auroral particles but in a controlled manner, successfully created localized patches or streaks of auroral light that could be observed from the ground or by accompanying optical instruments. These experiments allowed scientists to directly study the relationship between electron energy and emission altitude color, investigate plasma wave generation, and probe the electrical properties of the ionosphere. While far smaller in scale than natural displays, these artificial auroras provided valuable insights into the fundamental physics of how particle beams interact with the atmosphere to produce light, actively, though quietly, recreating a piece of the natural phenomenon for study. Fact 90. The aurora serves as a beautiful and direct visual confirmation of Earth's profound connection to the Sun and the surrounding space environment. It demonstrates that our planet is not isolated but is constantly interacting with the outflow of energy and particles from our star. The lights are a tangible sign of our magnetosphere at work, silently shielding us from the solar wind while simultaneously channeling some of its energy into a spectacular display. They reveal the presence of invisible magnetic fields guiding charged particles across vast distances. They highlight the composition of our upper atmosphere, acting as a natural screen that glows when energized. Watching the aurora is a quiet reminder that we live within a dynamic cosmic system, subject to the influences of space weather, and that even powerful forces originating 93 million miles away can manifest as delicate, silent beauty in our own polar skies, a luminous bridge between Earth and space. Fact 91. The height, or lower border, of an auroral arc or curtain provides a clue about the energy of the incoming electrons causing it. There's an inverse relationship. The more energetic the electrons are, the deeper they can penetrate into the atmosphere before depositing most of their energy through collisions, and thus the lower the altitude of the brightest emission. Very high-energy electrons, e.g., tens of keV, can reach down to around 90 to 100 kilometers, often producing intense displays with sharp lower borders, sometimes tinged with pink or purple hues from nitrogen excitation in this denser region. Less energetic electrons, e.g., 1 to 5 keV, don't have enough power to push as deep. They lose their energy primarily through collisions with atomic oxygen at higher altitudes, typically between 110 and 200 kilometers, producing the common, softer green arcs and curtains. Extremely low-energy electrons might only excite the very tenuous oxygen far above 200 to 300 kilometers, contributing to the faint, high-altitude red glows. Therefore, by carefully measuring the altitude of the aurora's lower edge, often using triangulation or specialized optical instruments, scientists can remotely sense the characteristic energy of the particles raining down from space, using the atmosphere itself as a kind of detector. A low-lying, sharp-bottomed curtain signifies a more energetic particle bombardment than a higher, softer green glow, a silent visual indicator of the power arriving from the magnetosphere. Fact 92. Auroral substorms typically follow a characteristic sequence of development, often divided into 3 phases: the growth phase, the expansion phase, and the recovery phase. During the growth phase, which can last for 30 minutes to an hour or more, energy from the solar wind is gradually stored in the magnetotail. On the ground, this might correspond to relatively quiet auroral arcs slowly drifting towards the equator. The expansion phase marks the sudden release of this stored energy, usually triggered by magnetic reconnect ion in the magnetotail. This phase is characterized by a dramatic brightening of the aurora near midnight, followed by a rapid poleward surge and westward expansion, the westward traveling surge. Intense, dynamic curtains, rays, and coronas often fill the sky during this explosive phase, which typically lasts only 10 to 30 minutes. Finally, the recovery phase begins as the energy release subsides. The aurora gradually becomes less intense and dynamic, often breaking up into more diffuse, pulsating patches or eastward drifting bands, and the oval slowly contracts back towards its quieter configuration. This entire cycle, lasting perhaps 1 to 3 hours, represents the magnetosphere's fundamental way of processing and dissipating the energy it continuously extracts from the solar wind, playing out as a silent, structured drama of light across the polar sky. Fact 93. The interaction of the solar wind with planets that lack a strong intrinsic magnetic field, like Venus and Mars, produces very different atmospheric phenomena compared to Earth's aurora. Venus has a thick atmosphere but virtually no global magnetic field. The solar wind interacts directly with its upper atmosphere, ionosphere, inducing electrical currents that create a weak, induced magnetosphere trailing behind the planet. This interaction can excite atmospheric gases, producing a faint, diffuse glow known as ashen light on Venus's night side, though its exact nature is still debated. Mars lost its global magnetic field billions of years ago but retains localized regions of strong crustal magnetism. When the solar wind interacts with the Martian atmosphere above these magnetic anomalies, it can funnel particles downwards, creating small, patchy auroral displays, primarily detected in ultraviolet light by orbiting spacecraft. These Martian auroras are much weaker and more localized than Earth's global ovals, occurring sporadically where the ancient magnetic remnants reach up into the thin atmosphere, silent, ghostly reminders of a lost planetary shield. Fact 94. The energy deposited by auroral particles not only excites atmospheric gases to emit light but also ionizes them, meaning it knocks electrons off the neutral atoms and molecules, creating pairs of positively charged ions and free electrons. This process significantly increases the density of charged particles, plasma density, within the ionosphere where the aurora occurs. This enhanced ionization is crucial for conducting the auroral electrojets, the horizontal electrical currents that flow within the auroral oval. Brighter auroras are associated with higher rates of particle precipitation, leading to greater ionization and thus higher electrical conductivity in the ionosphere along the auroral structures. This feedback loop, where the particles create the conductivity needed for the currents that are part of the system driving the particles, is a key aspect of magnetosphere-ionosphere coupling. The silent lights are therefore intrinsically linked to an invisible but dramatic enhancement of the electrical conductivity of the upper atmosphere, making it temporarily a much better conductor within the glowing regions. Fact 95. While most auroras are caused by particles originating from the Sun, via the solar wind, and Earth's magnetosphere, plasma sheet, cosmic rays, extremely high-energy particles, mostly protons and atomic nuclei, originating from distant supernovae or other astrophysical sources outside our solar system, constantly bombard Earth's atmosphere as well. When these highly energetic cosmic rays collide with atmospheric nuclei, they create cascades of secondary particles, a particle shower. These secondary particles can also excite atmospheric gases and produce very faint light emissions. However, this effect is generally negligible compared to the brightness of solar-driven auroras and contributes more significantly to the general background airglow. The energy scales involved are vastly different. Auroral particles typically have energies of keV, kilo electron volts, while cosmic rays can have energies up to eeV, exaelectron volts, billions of times higher. While cosmic rays silently rain down everywhere, their contribution to the visible night sky glow is usually overshadowed by the much more intense, geographically focused displays driven by our own sun. Fact 96. Cultural interpretations of the aurora often reflected the environment and beliefs of the people observing them. For coastal communities, like some Norse or Inuit groups, the flickering lights were sometimes associated with the spirits of marine animals like seals or whales, or reflections from schools of fish. For communities focused on hunting, they might be seen as the spirits of hunted animals or celestial hunters. The Sami people of northern Scandinavia traditionally viewed the aurora with caution, believing it was connected to the souls of the dead and that it was disrespectful or dangerous to draw its attention by waving or whistling. In Finland, a common folk tale explains the lights, revontulet, meaning foxfires, as being caused by a magical Arctic fox running across the fells, its tail sweeping sparks across the sky. These diverse interpretations highlight how different cultures sought to understand and integrate this powerful, silent natural phenomenon into their worldview, finding meaning in the celestial dance that shaped their northern nights, weaving it into the fabric of their quiet lives. Fact 97. The magnetosphere-ionosphere (MI) coupling is the complex system of interactions linking the vast plasma environment of space around Earth, magnetosphere, with the electrically conductive upper atmosphere, ionosphere. The aurora is perhaps the most visible manifestation of this coupling. Birkeland currents flow along magnetic field lines, transferring energy and momentum between the two regions. Electric fields generated in the magnetosphere map down along these field lines, driving currents and plasma drifts in the ionosphere. Conversely, conditions in the ionosphere, like its conductivity, which is enhanced by aurora, influence how the Birkeland currents close and can affect the behavior of plasma waves that propagate back out into the magnetosphere, potentially influencing particle acceleration and precipitation. It's a tightly linked feedback system. The silent lights we see are just one part of a continuous, invisible electrical and plasma dialogue occurring between Earth's atmosphere and its surrounding space environment, a constant interplay maintaining a dynamic equilibrium. Fact 98. The characteristic wavelengths, colors, of auroral emissions are so specific and consistent that they act like unique fingerprints, allowing scientists to identify the atoms and molecules involved and probe the conditions under which they are emitting light. The dominant green line at 557.7 nanometers and the red doublet at 630.0 636.4 nm are unmistakable signatures of atomic oxygen. The various bands of blue, violet, and red emitted by molecular nitrogen, N2, and ionized molecular nitrogen, N2+, also have precisely known wavelengths. By using spectrographs, instruments that spread the incoming light into its constituent colors, scientists can measure the relative intensities of these different emissions. This allows them to deduce properties like the average energy of the incoming electrons, higher energy favors N2 emissions relative to O green, the altitude of the emission, the temperature of the upper atmosphere, and even the relative abundance of different atmospheric constituents. Spectroscopy turns the silent beauty of the aurora into a rich source of quantitative physical information about the near-Earth space environment, decoding the light's hidden messages. Fact 99. Auroral displays often exhibit a preference for occurring during certain times related to magnetic local time, MLT, not just clock time. Magnetic local time is defined relative to the position of the Sun with respect to the magnetic pole. Magnetic midnight, 00 MLT, is the point on the auroral oval directly opposite the Sun. Magnetic noon, 12 MLT, is the point closest to the Sun. Auroral substorms typically initiate near magnetic midnight, with the expansion phase often spreading towards dusk, earlier MLT, e.g., 21 MLT, and dawn, later MLT, e.g., 03 MLT. Diffuse aurora is often widespread across the night side oval, while pulsating aurora tends to favor the morning sector, dawn side. Dayside auroras, linked to cusp precipitation, occur near magnetic noon. Understanding this MLT dependence helps scientists link the visible auroral features observed from a specific location to the large-scale processes occurring in different regions of the magnetosphere, e.g., reconnect ion in the tail near midnight, direct entry at the cusp near noon. It provides a spatial framework for interpreting the silent, evolving patterns of the global auroral display relative to the Sun-Earth interaction. Fact 100. Ultimately, the aurora is a profound reminder that Earth exists within the extended atmosphere of the Sun. We are constantly bathed in the solar wind, an invisible stream carrying energy and magnetic fields from our star across the vastness of space. Earth's magnetosphere acts as both a shield and a channel, mediating this interaction. The aurora is the beautiful, visible consequence of this continuous dialogue, the way our planet responds to the Sun's activity, dissipating a small fraction of the incoming energy in a harmless, luminous display high in our atmosphere. It connects the nuclear fusion occurring deep within the Sun, 93 million miles away, to specific quantum leaps in oxygen and nitrogen atoms 100 kilometers above our heads. It is a silent, grand, and beautiful testament to the interconnectedness of our solar system, a celestial light show demonstrating the fundamental forces that shape our cosmic neighborhood and protect the fragile biosphere that allows us to witness such wonders in quiet contemplation.